Let's learn the basic principles of BJT. A small current at the base controls a larger collector current. This is the key to instrument signal amplification, very vital for precision instrumentation applications.
Imagine a heavy steel valve on a giant industrial pipe. With a gentle twist of your wrist, you release a massive, high-pressure rush of water. Your hand doesn't provide the energy, it just controls the gate. This physical relationship is the best way to understand a bipolar junction transistor, or BJT. Instead of water, it uses a trickle of electricity to control a massive surge of power, and it does this with zero moving parts to break or wear down. This ability to manipulate heavy power with a tiny electrical nudge is the invisible bridge between delicate computer brains and heavy physical machinery. To see how they are built, we can map the three terminals of a transistor directly to our plumbing system. The collector is the water supply, the emitter is the drain, and the base is the valve. Sending a tiny drop of current into the base opens that main gate, allowing a massive rush of electricity to flow. Engineers call this multiplier beta. If a transistor has a beta of 100, it means 1 unit of electrical current at the base unlocks exactly 100 units through the main pipe. Beta is the precise metric that dictates how much muscle a weak sensor can flex when it is connected to a larger circuit. We can use this valve metaphor to see the transistor's three states. In cutoff, there is zero base current and zero flow. The valve is tightly shut, acting as a complete off switch. Then there is saturation. Here, a strong base signal makes the valve fully open, allowing maximum flow. This makes it an on switch. In the middle, we have the active region. The valve is only partially open, allowing small wiggles of the handle to create much larger waves in the water flow. This turns the transistor into an analog amplifier. Controlling these three states allows the same component to handle completely different jobs, from binary logic in a laptop to volume control in a radio. Physically, BJTs are constructed as multi-layered sandwiches of semiconductor materials, which engineers label as N-type and P-type. We group them into two types, NPN and PNP, depending on which direction the primary current is designed to flow through those layers. On a circuit drawing, you can identify them by looking at the arrow on the emitter. For an NPN transistor, the arrow is not pointing in. For a PNP, it is pointing in. Having these two mirrored versions gives electronics engineers the flexibility to route primary currents dynamically across complex circuit boards. Even though these are powerful, the base terminal is delicate. Applying raw power directly to the base without restriction will instantly destroy it. This circuit uses a base resistor to act as a bottleneck. It strictly limits the control current to safe levels so the transistor can switch an LED without burning out. There is another danger when switching off heavy loads like a motor. As the magnetic field inside the motor collapses, it creates a massive splashback of voltage that can slam back into the circuit. To stop this, we use a flyback diode. It acts as a protective bypass lane that safely absorbs that electrical shockwave before it can hit the transistor. Building these circuits requires managing the physical force of electricity so that a sudden surge of power doesn't turn the transistor into smoke. A BJT can be wired in three primary ways: common collector, common base, or the most popular choice, common emitter. In this common emitter setup, the input goes to the base and the output is drawn from the collector, making it the perfect signal amplifier. It also creates a phenomenon called phase inversion. As the base handle opens and water rushes down the drain, the pressure at the top of the pipe instantly drops, so as the input goes up, the output goes down. The other setups serve specific roles. Common collector is great for stabilizing voltage, while common base is used for high-frequency radio signals. By simply rotating how those three pins are connected, the exact same component transforms to solve completely different problems. There is one final challenge. Semiconductors are sensitive to heat. As they get hot, the electronic valve becomes sticky and its performance drifts unpredictably. Engineers solve this using biasing. This specific network of resistors shown here locks the transistor into a stable operating point, regardless of how hot the device gets. At its heart, the transistor is about taking a tiny, weak signal and using it to safely trigger a heavy-duty response. It is an electronic faucet, turning whispers into roars and tiny calculations into real-world action. Every computer, smartphone, and industrial machine relies on this interaction. Have you ever stopped to wonder how a tiny, super delicate digital sensor, maybe something monitoring seismic activity or temperature, can command a massive industrial water pump to just switch on? I mean, how does a whisper of an electrical signal control a roaring machine? Well, the answer lies in a microscopic, three-legged piece of silicon. Welcome to this explainer on the Bipolar Junction Transistor, or as we call it, the BJT. Today, we're going to demystify this incredible little component and see exactly how it acts as the ultimate digital valve. Okay, let's dive into this. Here's our roadmap for today. We'll start by meeting the BJT, break down its anatomy and schematic symbols, and learn how it actually controls current. Then, we'll prep it for action with biasing, watch it function as a high-speed switch, and finally wrap up with a deep dive into its absolute zero state, the cutoff finale. So, Section 1, let's officially meet the BJT transistor. You know, this tiny piece of tech is literally the foundational building block of modern electronics. If you've tinkered with basic diodes, you probably know they act kind of like a one-way street for electricity. But the BJT, it has 3 terminals, which makes it a highly complex, active component. It's a total multitasker. It acts as an amplifier to boost tiny sensor signals, a driver for heavy relays and actuators, a high-speed electronic switch for load control, and even a signal shaper for precise data acquisition. Pretty cool, right? Moving right along to Section 2, anatomy and schematic symbols. And this brilliantly illustrates what's actually going on under the hood. You've got the physical PN semiconductor layers on one side and their schematic symbols right next to them. Notice the 3 terminals, the collector, the emitter, and the base. Now, look really closely at that base layer in the middle. It is incredibly thin. If you think of the collector and emitter as a massive water pipe, that super thin base is basically the delicate valve handle controlling the flow between them. You'll also see 2 distinct flavors here, NPN and PNP. That just refers to the specific arrangement of the semiconductor materials. Honestly, remembering which symbol is which can be a bit of a headache. So let's borrow a classic mnemonic rule. Just look at the little arrow on the emitter terminal. For NPN, the arrow is pointing out, so just think not pointing in. And for PNP, the arrow points inward, so think pointing in proudly. It's a ridiculously simple visual trick, but trust me, it saves you so much time when you're trying to read complex circuit diagrams. All right, Section 3, controlling the current. Let's look at the physics of how this thing actually works. This formula right here, it's the golden rule of the BJT. The total current flowing out of the emitter is simply the sum of the current flowing into the base plus the current flowing into the collector. But remember our water valve mental model from earlier? The base is that super thin handle. It takes just a tiny trickle of base current to completely open the floodgates, allowing a massive Russian collector current to flow straight through to the emitter. And to put that into perspective, how massive is that difference? Well, a typical beta value, which is just the term we use for the transistor's DC current gain, is usually around 100. That means if you push just 1 single microamp of current into the base, it allows 100 microamps to flow down through the collector. The base is essentially multiplying its own current by 100 times just to control the main load. It's doing a lot of heavy lifting. Which brings us to Section 4, biasing and operating regions. This is all about prepping the transistor for action. A standard silicon BJT actually needs a little push, about 0.7 volts at the base, just to wake up. Setting up these initial voltages and currents is what we call biasing. Now, this fixed bias circuit is the absolute simplest way to do it. It just uses a base resistor and a collector resistor. But while it's super easy to build, it's also highly vulnerable. Even slight changes in temperature or just natural manufacturing quirks in that beta value we just talked about can throw this whole circuit completely out of whack. Let's move to VE and see how this builds into something far more robust. See the difference? We've added a single resistor to the emitter labeled RE. This brilliant little tweak provides something called negative feedback. If the transistor tries to run away and draw way too much current because it's getting hot, this resistor creates a voltage drop that essentially chokes off the base. It automatically stabilizes the whole operation. It's a total game changer. Depending on exactly how we bias the transistor, we basically force it to live in one of 3 states. First is cutoff, where it is completely 100% off. Second is the active region, where it lives as a proportional amplifier. And third is saturation, where it's fully on, like a valve cranked entirely open. For the rest of this explainer, we're going to skip the amplifier theory and focus entirely on the extremes, cutoff and saturation. On to Section 5, the BJT as a switch. We are officially entering the realm of binary control. So here, the transistor isn't amplifying a smooth, wavy signal. Nope, it's a harsh binary controller, either stubbornly off or violently on. And the step-by-step logic of a digital on command is just a thing of beauty. First, your microcontroller sends a high voltage, usually around 5 volts, hitting that 0.7 volt wake-up threshold. Second, base current begins to flow. Third, this tiny current instantly forces the transistor into saturation, snapping our theoretical water valve wide open. And finally, step 4, the main current rushes through the collector, instantly activating your load. Let's map those exact steps onto our real circuit. Here, we have a BJT switching on an LED. Your input signal comes in from the left. Now, notice the base resistor, RB. This is absolutely critical. If you left RB out, the base would try to draw infinite current, and the transistor would just instantly pop. Goodbye, magic smoke. RB restricts that flow, giving the transistor just the perfect amount of current to reach saturation and turn the LED on safely. Now, what's really interesting about this next setup is the component labeled D1, the flyback diode. Here, the BJT is driving a heavy electromagnetic relay coil. The thing is, when you turn a relay off, the magnetic field in the coil suddenly collapses, which violently fires a massive voltage spike backward. That spike, it would instantly assassinate our delicate little transistor. The flyback diode catches that nasty inductive spike and safely loops it back into the coil, keeping our BJT perfectly safe. And finally, Section 6, the cutoff state finale. You know, turning a transistor off is just as critical as turning it on. Let's contrast these two extremes. In saturation, the valve is fully open. Both junctions are forward biased. The voltage across the transistor drops to near zero, and current just flows freely. But cutoff is the exact opposite. To achieve cutoff, the voltage at the base is dropped completely below that 0.7 volt threshold. The valve isn't just closed, it's perfectly sealed shut. The base emitter is reverse biased, the base current is effectively zero, and because of that, the massive collector current is completely choked out to zero. I want to guide your eyes to the very bottom of this output characteristic graph. Do you see that dashed line running flat along the bottom zero axis? That right there is the cutoff region. Without any base current to push the valve open, the collector is completely physically isolated from the emitter. Honestly, no matter how much voltage you have waiting at the collector, up until the silicon literally breaks down, absolutely nothing is getting through. So the crucial point is this. Cutoff isn't just some casual off state. It is a state of absolute physical isolation within the semiconductor crystal. It ensures the circuit behaves as a truly open switch. And this flawless isolation is exactly what protects sensitive digital systems, ensures heavy industrial loads don't accidentally turn on, and guarantees that a digital zero truly means zero. But before we wrap up, I want to leave you with a fascinating vulnerability to ponder. We know that the cutoff state completely relies on the base voltage staying below 0.7 volts to maintain that perfect digital zero, right? But think about a noisy, real-world industrial environment. What happens if stray electromagnetic interference, or just a burst of static, briefly spikes that base wire to, say, 1 volt? Well, the perfect seal breaks, the valve twitches open, the massive machine might suddenly stutter to life. The absolute perfection of digital computing logic is ultimately completely at the mercy of analog physics. Definitely keep that in mind the next time you're designing a circuit. Thanks so much for joining me on this explainer, and keep exploring.